Hi and welcome back to Little House of Science. My name's Ollie and today we're going to be learning all about the science of change. We're going to be learning about chemicals and chemical reactions. Let's begin by asking the question, what is a chemical? Have a little think to yourself. What do you think the word chemical means? A chemical is a substance with a set number of ingredients. Change one of those ingredients and you have a different type of chemical. Some chemicals can be stable and others are unstable. Different chemicals have different levels of reactivity, and we're going to be mixing lots of different chemicals together today to see what happens. Think about what chemicals are. I like to think about cakes. Now, if you baked a cake before, you know you need to follow a recipe. A cake recipe will have things like eggs, flour, butter, sugar, maybe some chocolate. Now, if you change one of those ingredients, let's say we didn't have any chocolate, so I went outside into my garden and I found the first thing that looked just a little bit like chocolate, some soil, and I mixed that in with my batter and baked it. Would I still have a chocolate cake? Absolutely not. I would have a dirt cake, something completely different. So chemicals need to have a very specific list of ingredients. You change one and you change the chemical. So in chemistry, we don't use those regular baking ingredients. Instead, we use what's called the periodic table of elements. These are all the different types of atom we find in the universe, and it's with these that we make chemicals. You may have heard of many of the different types of elements, like gold, silver, copper, zinc, perhaps, even iron, magnetic iron. There are over 100 of them. Now, mixing them together can have all sorts of interesting consequences. Let's take two examples and see what happens when they come together. The first example is sodium. Sodium is a metal so soft you could cut it with a knife. But don't let its softness fool you, it's highly reactive. If you take sodium and place it in just plain old water, it will explode violently. Now let's mix that with another atom, chlorine. Chlorine is what they use to clean swimming pools in very small amounts, but in large quantities, it is deadly poisonous. It is a horrific gas. It can even blind you if it gets in your eyes. Now mix explosive sodium and poisonous chlorine together, and what do we get? Plain old salt. Salt is perfectly stable and happy and very much unreactive. This is just one of the many magical things that happen when we know a little bit about chemistry and what happens when we create these interesting new chemicals. So what we're going to do next is we're going to take two full chemicals, we'll talk about their ingredients, the atoms that make them, and we'll mix them together and see if we can make something new. And that is the heart of a chemical reaction, making something new. Chemical reaction, you need your reactants. They are the chemicals you're going to mix together. Once they're combined, they should produce your products, the things you've made, and these products will always be different to your reactants. In every chemical reaction, there will be some exchange of energy, often in the form of heat. So we're going to pay attention to the temperature of our reaction as well as what's just made. So in this reaction, we're going to do a very classic one. I have a balloon filled with sodium bicarbonate, and over here I have some vinegar, which contains acetic acid and water. When I mix these together, let's see if we make something. I've placed this in a balloon because I know we're going to create a gas. And gases, they will expand to fill whichever volume they're in, so I'll need to capture them inside of this balloon. Put in the bicarb, and it fills all the way up and fills up my balloon with carbon dioxide gas, one of our products. I keep stirring this around, making sure that all of my reactants have managed to react with each other, and let's see what we create. So we've definitely got lots and lots of gas, carbon dioxide, seems to have bubbled away. Now we've got what looks like water or vinegar in the bottom here. This is in fact water down here. There's no more acetic acid left, just water. And there is a fine white powder at the bottom, but that isn't sodium bicarbonate. Instead, that is something called sodium acetate, which is a type of salt. I'll take this off. And now I have a balloon completely filled with carbon dioxide, one of our three products. I tie this up. We can experiment with its density. Carbon dioxide is much heavier than oxygen or nitrogen or the other components of the air around us. So this balloon is a very, very heavy one, even though it's still filled with gas. If you do this reaction at home, a really fun game to play is to try and keep the balloon up in the air for as long as you can without dropping it. It's very difficult because the balloon is so dense. So let's move on to other types of chemical reaction. We have endothermic reactions. Is there such a thing as an exothermic reaction, a reaction that gives out heat rather than taking it in? The answer is yes. Exothermic reactions are often things like explosions and fireworks, things that produce lots and lots of heat energy. Here is a little tiny one. This is the middle of a Christmas cracker. There are two strips of card, and in the middle there is an overlap which has been sealed with some tape. On the very ends of each of these strips there is something called gunpowder, a combination of very explosive powders mixed together. All we need to add here is a little bit of friction to get the reaction started. When you pull a Christmas cracker, you make the two ends slide past each other, heating up the gunpowder, and you create a little tiny explosion, an exothermic reaction. Here we go. In these last two chemical reactions, we saw signs that the reaction had taken place. It could be gas bubbling or foaming, or it could even be, in the last one, an explosion. But there are other signs of chemical reactions too. Now let's talk about the importance of colour change. The chemical we're about to look at now, I got in a very strange way. This purple liquid here is what I got when I cut up a red cabbage, poured some hot water over it, and then strained off the water. So this is just red cabbage water, but it's very interesting stuff. Doesn't smell so good though. Now, when I mix this with either an acid, that's one type of chemical, or an alkali, it's another type of chemical, it will change colour and it will indicate to us which one we have, acid or alkali. So let's start off with this liquid here. Now red cabbage water will go pink or red if it touches an acid. So let's see what kind of substance we have in this pot. Well, this lovely pink colour shows me that I've definitely got an acid, and if I smell it, it's vinegar, so we know for sure we have an acid over here. What about if it touches an alkali? So over here, I've mixed in some baking soda with water. Let's see what kind of colour change we get. So cabbage water will turn blue if it touches an alkali. Now what we're going to do next is we're going to mix these together to see what happens. See if there's any more colour changes that we can get. Let's mix them and see what happens. Definitely a lot of fizzing and bubbling, and our what was pink vinegar is now turning purple again. So we're turning back to what we had at the beginning, purple. This sort of makes sense because if you mix blue and red together, you get purple, but there's something a bit more complex going on here. This is what's called a neutralization reaction. And to explain that, we need to learn a little bit about what an acid is and what an alkali is, and also what a neutral chemical is. So in the next section, we're going to talk about this special range of chemicals along what's called the pH scale. Chemicals sit somewhere along the pH scale. It ranges from 0, where we find the strongest acids, up to 7, which is in the middle, where we find neutral chemicals, and right up to 14 at the other end, where we find the very strongest alkalis. Chemicals with a value of 0 or 1, or 13 or 14, are incredibly dangerous. They are the strongest acids and alkalis in the world. They are all completely toxic to humans and dangerous to touch. To understand why we group chemicals along the pH scale, we need to learn a little bit more about atoms. Atoms, we remember, are those little building blocks that all chemicals, and in fact everything around us, is made from. Atoms themselves also have their own little tiny ingredients list. Atoms, though, are always made of the same 3 ingredients. The only thing that changes from atom to atom is the number of these 3 ingredients that they contain. These ingredients are protons, neutrons, and electrons. Protons have a positive charge, and they are held together in the center of an atom by the neutrons, which have no charge at all, but do exert a force that's strong enough to hold the positive protons together. We have to remember that positive charges should always repel each other, so the neutrons are necessary to keep the protons clustered together in the middle. We call this central cluster in an atom the nucleus. Now, where do electrons fit in? Electrons, they have a negative charge, so they are attracted to the positive nucleus. But electrons also repel each other. So when electrons come towards our central nucleus, they are repelling each other constantly, and therefore they move around and spin around the outside of our nucleus. And that is what makes up an atom. Our electrons whizzing around the outside of our protons and neutrons in the middle. Acids are chemicals which are able to give some protons up. They will give off or donate protons away. Alkalis receive protons. So we have acids that donate and alkalis that receive. When we mix an acid and alkali together, we see always a neutralization reaction where those protons are given and received, and often we'll find something new being created by this passage of charges. So why do we call it the pH scale and not, say, the proton scale? pH stands for power of hydrogen. Hydrogen is element number 1, and it's a very important element. We call it element number 1 because it has just 1 proton and therefore 1 electron, and no neutrons are needed. If a hydrogen atom loses an electron, it is essentially just 1 proton on its own. But we can also call it a hydrogen ion. An ion is any atom that has lost either a proton or an electron, so it has a charge. It needs to get one of those little ingredients back again. So a hydrogen ion, or H+, is just a proton on its own. And that's why we call it the power of hydrogen. What we're really saying is the power of hydrogen ions, whether a chemical has lots of ions to give away or it wants to receive hydrogen ions. Now that we've done some chemical reactions, let's see if there are any other types of reactions out there. The next type of reaction we're going to look at are called physical reactions or physical changes. Here we start off very much in the same way. We have different chemicals and we mix them together. But in this instance, we don't create anything new. All we're going to do is change what our reactants look like, change their physical properties in this reaction. So a physical change doesn't create new products, but it changes what our reactants look like. Let's have a look at some examples. In our first example, we're going to mix a very special chemical called acetone with plastic. Acetone is a neutral chemical that is also called a solvent. Solvents are chemicals that can dissolve other things, and acetone is really good at breaking up different types of plastic. So let's have a look at this example. I have some pungent acetone in this bowl here. You'll notice this is a plastic bowl I'm keeping it in, so that shows us that acetone doesn't break up all plastic. But over here I have a styrofoam cup. This is a special type of plastic that's been inflated with air. It makes it really insulating, so I can fill this with boiling water and not burn my hands because the air inside the plastic keeps my hands safe from the heat inside. But let's see what happens when we mix them together. Let's see if we can create something. I can hear some fizzing and see some bubbling, but what you can probably see here really easily is the cup is seemingly disappearing into the acetone. It looks like some kind of magic trick. But what's happened is the acetone has broken some of the bonds in our plastic and allowed the air to escape, and that's what the bubbles were. What we're left with is a strange plastic sort of slimy goop. It almost looks like old chewing gum that's left over. Now this looks like a chemical reaction, but it was only a physical change, because although it looks like our cup has vanished or been smashed to pieces, it is still plastic. This is still a lump of plastic. It just looks very different. So this here is a physical change, not a chemical reaction. Let's look at another example. In that last reaction, we broke down some bonds in plastic. Plastic is an example of a chemical called a polymer. And when we snip down those different chains inside the plastic, we call the reaction a depolymerization. Now, it's important to mention that we should never touch acetone. It's in fact a very dangerous chemical, but sometimes people use it to remove nail varnish from their fingers because it breaks down the plastics in nail paint. Now, in this reaction, we're going to do the opposite. We're going to see if we can build up a polymer, or a big chain of molecules, from lots of individual ones. These individual molecules we call monomers in this case. The monomers we're going to be collecting are in this sort of nasty purple sludge here. This I made from something called sodium alginate. It's a little powder you get from seaweed. When you mix it with water, it makes this jelly. Now, the reason why it's purple is a secret, and I'm going to tell you why it's purple in a moment. To make this into a polymer, we need to expose it to a salt that contains a very special metal called calcium. Now, you might have heard of calcium before. It's what makes our teeth and bones strong. So I'm going to draw some of this sludge up in a syringe, and I'm going to add it to a mixture of calcium lactate that I made earlier. After just a few seconds, we'll notice that what was once a liquid is now a solid. We have a solid jelly worm of our sodium alginate. The calcium lactate has caused links between the monomers of the sodium alginate and turned it into a long polymer. I can make lots of these in here, so I'll make another one. And what I love about this experiment is that it happens almost instantaneously, but it's always best to leave our sodium alginate in this mixture for as long as possible. The longer it's in there with the calcium lactate, the harder the polymers will become, until they're almost as strong as a piece of rubber. So I'll leave those in here for a little bit. It's worth mentioning for this reaction, all these chemicals are perfectly safe. That's why I'm putting my fingers in so bravely. So these are what we've made, these long strands of sodium alginate. So it's now time for me to tell you why they're purple. When you make sodium alginate solution, you mix it with plain water. But in this instance, I didn't use water. I used cabbage water, which remember, is that very special mixture that we can use to see if something is acid or alkali, which means that these jelly worms here should change color if we place them in an acid or an alkali. So let's see if that works. I've got some acid, some more vinegar over here. I'll take some of these worms and I'm going to place them inside and leave them for a while in with the vinegar, and let's see if they change color. I'll take some of the old ones to compare. So here are the old ones, purplish, slightly translucent. And here are the pink worms we've just made. So these pink ones have shown us that we have an acid. We've got vinegar. They've gone pink. And if I can compare those to these ones over here, these are purple. So we've got pink and purple. So we've got color changing jelly worms. I could even place this in a mixture of baking soda to see if they go back to purple again with a little bit of fizzing, just in case there's some vinegar on the outside, they may fizz. So these color changing jelly worms are made from a solution of sodium alginate and cabbage water, and I mix them, I polymerize them in another mixture of calcium lactate and water. us. Some are formed naturally, others are formed by scientists, and they can be used for all sorts of incredible purposes. And let's remember that chemicals are made out of a set list of ingredients, and those ingredients we call the atoms, and those atoms we find on the periodic table, listed from number 1, hydrogen, all the way through to over 118. There are over 100 of them. Mix those together, we make chemicals. Mix chemicals together, and sometimes we get chemical reactions, or we make brand new chemicals that we call the products of the reaction. And in every chemical reaction, there is some exchange of energy. If heat energy is taken in, it is an endothermic reaction. And if heat energy is given out, it's exothermic. I hope you enjoyed this video, and I hope you see you again in the next one. Don't forget to like and subscribe, and I'll see you again next time. Bye, everyone.